Hi everyone. So it's perhaps a slightly contentious title to this video in that not everything is quantum. Some would argue otherwise. What do I mean by that? And what was that SMBC? And if you're not familiar with SMBC, go and look it up. No, SBMC. Saturday morning breakfast cereal, right the first time. Go and look up SBMBC. Some fantastic cartoons, some of my favourite cartoons, even rivaling XKCD at times. What was the point of that? Well, they were drawing the distinction between something that's discrete and something that's quantum. And those two terms are mixed around a lot. Now, we are kind of a quantum system, but that doesn't mean that it has to have discrete eigenstates. What do I mean by that? Well, trust the old particle in a box as ever. I'm not going to draw out everything. I'm just going to draw the energy levels. So, got the n equal to 1 energy level, n equal to 2, and n equal to 3 energy level. So n equal to 1, n equal to 2, n equal to 3. Discrete energy levels. And our basis for this is a discrete, so we can represent our wave function as a discrete sum of, let's call those Cn by, and what we call it, let's call it Un for clarity. So, we can represent our wave function as a discrete sum of the eigenfunctions with a certain mixture, certain coefficient that determines how much of that eigenfunction is in our state of our system. Banged on about that at length in previous videos. The point I want to make here is that this is discrete. Our energies are given by n squared h squared over 8ml squared. So this is very much discrete. So this will be E1, this will be 4 times E1, and this will be 9 times E1. Let me just separate this out. Okay, everything on there? I think it is, yeah, good. Discrete energy levels. So we've got a set of eigenvalues that are discrete, well separated numbers for the energy. And similarly, a set of eigenfunctions that we just build them up from a discrete set. We take this amount of the first one, this amount of the second one, this amount of the third one, etc., etc. One of you asked, why do we stop at the third? Why don't we have an infinite set? Well, it depends on the system. We could have one eigenstate. The system could be in one eigenstate. The system could be in a superposition of 3 eigenstates, or 10, or 100, or 1,000, or 1,000,000. It depends on the system. So, these are eigenstates of the Hamiltonian. If I draw the wave function in again, you know what it looks like. I'll just draw it like this on those. Those are stationary states. We saw, if you go to the back in the box, we saw in the last video, the video before that, of one of the previous videos. Back in the box 1 and back in the box 2. Select the system so it's in an eigenstate of the Hamiltonian. Eigenstate of the Hamiltonian, assuming our Hamiltonian is time independent as it will be for everything we treat, is a stationary state. It doesn't change in time. You saw this. The real and the imaginary parts change because of the phase term, which depends on time. But the probability density doesn't care about the phase, therefore it's stationary in time, and therefore all observables that depend on the probability density are also independent of time independent. So if the system is in an eigenstate of the Hamiltonian, it's in a stationary state. But not every state is an eigenstate of the Hamiltonian. We saw a few videos ago that we can add up different superpositions of states, but also we don't just have to work in that basis. We can represent our wave function, not just in terms of the eigenfunctions associated with the Hamiltonian operator, but we can represent our wave function in terms of the eigenfunctions associated with the position operator or the momentum operator. It's like having some object and you're sort of shining a light on it from different directions. You're casting some projection, and we'll be seeing later on how that projection analogy is very important a couple of weeks down the line when we go to matrix mechanics. We've got some projection, and from that projection we can look at our wave function in different ways. So that's a discrete state, but a discrete basis. We can also, of course, have a continuous basis. What do I mean by that? Okay, I've cleared everything off the board, just leaving that. It's very important to note that the reason we have this discrete basis, the reason we have this discrete set of eigenvalues is because we've confined the system. We've set up our boundary conditions, and it's that gives rise to the quantization of energy. It's the fact that we've got those boundary conditions in place. If we don't have those boundary conditions in place, then what we have, instead of having our sign type, instead of having eigenstates that look like this, if there's just no boundary condition, if the electron is free to wander across the entire universe, or free to be found across the entire universe, then what we end up with are basis functions of this form. Now, there are no constraints on this value because there are no boundary conditions. So there are no constraints on this particular value. The reason we get this discrete set of eigenfunctions and eigenvalues is entirely due to the fact that we've quantized the system in that we've confined the electron. And once we do that and we set those boundary conditions, that means we have only select certain solutions that will fulfill the boundary conditions. That's what gives us the quantization. Without those boundary conditions in place, well, we can take this as our form of our eigenfunction. Let's make sure, does this satisfy the eigenvalue equation for the Hamiltonian operator, which, given that this is a free electron, there's no potential, will just be of the form there. No potential in free space. Does this satisfy this? Well, if we differentiate this once, we'll have d dx of that is ik a e to the ikx, doubly differentiated. Well, we're going to have minus k squared a to the ae x. Plug that into our full operator, then what we have is that if we have h, our Hamiltonian operator, acting on ae to the ikx, let me just clear that off so it doesn't get in the way. Hamiltonian operator will give us h bar k squared over 2m with our original function returned. So, yes, this type of function is an eigenfunction in a Hamiltonian operator. I should say kinetic energy operator in this case because we have no potential energy term. Everything changes when we add in the potential energy term. But in this case, with v equal to 0, this is eigenfunction of the operator with this eigenvalue. And this eigenvalue, this holds for any value of k. There are no constraints on the value of k. Similarly, we have, if we think about the momentum operator acting on this function, we have minus I h bar d dx operating on a e to the I kx gives us back h bar k. We'll differentiate, that's not a minus. We're differentiating this, so we've got ik comes in front. Minus I by I gives us 1 here, and the k goes with the h bar, so we get h bar k, ae to the I kx, and that's just p ae to the I kx. So this and I'm stressing this very, very much, in the case of a free particle, v is equal to 0 with no boundary conditions. So just let me stress this. So we have ae to the ikx. Functions of that form are eigenfunctions of both the momentum operator and the Hamiltonian for a free particle. That doesn't just mean that v is equal to 0, it means there were no boundary conditions. And only in that case, with v equal to 0, no boundary conditions, is this both an eigenfunction of this and this operator. We will be coming back to that. Right, so let's just focus on the momentum case, momentum operator for the time being. Because any value of k will work to satisfy the eigenvalue equation, unlike the case for the energy eigenvalues and eigenfunctions for the particle in a box case for the Hamiltonian, where those are discrete levels. In this case, any value will do. So it's very, very, very similar indeed. In fact, it's exactly the same mathematics as when we talked about Fourier transforms and we talked about the discrete Fourier transform in terms of having something that looks like this, where we can represent our function. Oh, let me put it this way, put it in the middle. Discrete, where we'd represent a function like this, however many terms it takes. And our spectrum is a discrete spectrum. And notice I'm using the word spectrum in analogy with energy spectrum or light spectrum. Why do we why do we call it a spectrum? Because we break the light down into particular energies. It's exactly what we have here. So our spectrum in this case would be discrete. We'll have, so these are our Cn values, or magnitude of Cn. And here is omega on this axis, but it's omega 0, 2 omega 0, 3 omega 0, 4 omega 0, etc. It's discrete. But we know that in the event where we don't have discrete separations of these frequency components, and that means we don't have a purely periodic function, then we no longer write our function in terms of a basis, a discrete basis like this. We have to write it in terms of, well, actually, we have to write it in these terms. Let me put that to remain consistent. What we're doing here is representing our function in terms of a discrete set of functions. But here, we're representing our function in terms of a continuous distribution, where instead of having a delta omega effectively here, where delta omega is omega 0, 1 omega, etc., we've got the space in between these is omega 0. Here, as I've said before, we've no longer got a discrete, finite delta omega, we've got a d omega. And relating that back to the eigenfunctions of the momentum operator in the case of the free particle, or the eigenfunctions of the momentum operator in general, then because we can have any value of k that satisfies that particular eigenvalue equation, it means our values are continuous. Our values of k are continuous. We're not constrained to particular discrete eigenvalues. Okay, so that was in context of time. Let's move back to just connect you back with what we did with Fourier transforms a while ago, just to show you that it's the same mathematics, it's the same ideas. Let's now couch this in the context of k and momentum. So, because k can be any value, what we can't write is this. We can't write, and let's do it like this. We can't write our wave function like this. We can't do this. Can't do this. Because we don't have a discrete set. We can have any value of k. So, instead of having that, and let's get it off the board as quickly as possible, what we instead have to is write our wave function like this. Can we see that? Oh wow, I think it stays on the board. Cool. That's our Fourier transform. So if we want to get the position, if we want to get the momentum representation of the wave function, we take the Fourier transform. That gives us this. But that's equivalent to saying, well, how do we represent our position representation of the wave function? Well, what it is a Fourier integral. It's exactly the same concept as when we had on the number of questions we've done in terms of when we get the wave function, or we think about a superposition state for the particle in a box, where we're just summing up and mixing together and changing the coefficients to control how much of each eigenfunction we have in the mix. It's exactly the same thing, but except we no longer have discrete. We have an infinite range where this value of k can be is continuous. It's not discrete. So I know conceptually it's perhaps a little bit challenging, but just get your head around that idea of the difference between a discrete spectrum, like we have for the Hamiltonian, the energy eigenvalues for the Hamiltonian particle in a box, to a continuous spectrum, which looks like this, which means that in this case, we'll have an integral and we'll have a function. Rather than specific values, we have a function. Let's look at that in the context of the particle in a box again. I know I keep coming back to the particle in a box. I know you're probably tired of hearing about it, but so much of quantum is in that particle in a box, and there are still subtleties. Some of you have been emailing me actually, and there's some interesting subtleties in terms of the particle in a box that you really have to think carefully about. And I certainly, as an undergraduate and even as a postgraduate, as I've told some of you, really didn't get my head around them. So let me just talk you through this. So our momentum distribution is continuous, not discrete. So, particle in a box. Let's just think about the ground state. And I actually asked you to do this. It's on one of the worksheets, and I've given you a detailed breakdown of the solution, including plotting out the stuff I'm about to sketch out on the board. Don't rely just on the notes. Those worksheets are really important. And the worksheet solutions contain a lot of information that backs up what's in the videos, that backs up what's in the notes. I don't want to, deluge and bury you in tons of material, but all of these things do connect together. And I'm trying to come at it from different angles because I know these concepts are not easy. I'm trying to come at it from as many different angles as possible so that maybe one of those approaches will work. So make sure you look at the solutions to the worksheets. I know, I did this as well too. I know the exam seems quite some time away, but try and keep on top of the material as we're going along. But I also appreciate that you've got other drawers on your time, so it's a question of balancing all these different activities that you've got to do and the different pressures on your time. Right. So we're just going to look at the ground state. So it looks like this. That's our wave function in the position representation. But we can equally well look at this wave function in the momentum representation. And the way we do that is we Fourier transform, ft for Fourier transform. And let me just sketch this for absolute clarity. Although within the box, that's meant to go to 0 there and there. Although within the box, this is our x-axis along here, the particle wave function is described by a sign. As I've said in one of the synchronous sessions, it's not a sign over all space. It's a sign in those limits, and it's 0 beyond those limits, which means that when we Fourier transform this, we're going to have a fairly, it's not going to be as simple, just a couple of spikes, just a couple of delta functions, because these aren't long extended, infinitely extended sine waves. We're going to have to account for, we need lots and lots of spatial frequencies here and here to add together to actually cancel this out. So it turns out that when we do that, on the other thing, let me actually plot this like this instead. It's just going to look roughly the same, but it looks a bit more like that. So that's our probability density in the well. We can Fourier transform that, Fourier transform a wave function, and then get and that's going to look something like, yeah, so let's leave it. That's like, can we see that? Yeah. So we have a probability density in the well, we Fourier transform that, and we get our, let me put it up there. We get our probability density, but in momentum. So a number of you have asked, well, what's the probability of getting momentum? How would we do that? Well, we can use our operators to get measures of the, expectation values, etc. But if we want to work out what's the probability of finding a momentum within a particular range, what we can do is we can do exactly the same approach as we have here. If we wanted to know what the probability of finding this particle on one side of the well is, then we'd integrate under here. Similarly, if we want to know what the probability of this particle having positive momentum is, well, we'd integrate under that. Wonderful aspect of Fourier transforms, if we get our normalization correct, is that this is normalized and we Fourier transform, this is normalized as well. So this is a half in terms of finding the particle on that side, but we've got a probability of finding the particle with k, positive k, i.e. positive momentum. We've got equal probability of finding it with positive or negative wave number. So that means it's equally probable to be going that direction as that direction, which is, if we want to push it onto a classical problem, it's, if you think about a ball bouncing back and forth in a box, it's likely to go that way as it is to be going that way, because it's bouncing back and forth up the walls. But notice, this is not just one momentum. This is a continuous distribution of momenta, because in the case of the momentum eigenstates, those eigenstates are plane waves. Those a of the form e to the ikx. And so we know that if we've got plane waves, we had to add them up in the right way to reproduce, to get our wave function, which means we're not going to get discrete values of k for the particle in a box. Go back, watch the video, think about this, go and in particular read the solutions to worksheet. I think it's the last question, I believe, on worksheet 4, question 5 on worksheet 4. Read that and read read the question and read the solution, and hopefully that will help. As ever, a number of you have contacted me about this already, which is why I'm spending some time on it. But I hope that helps. So, drawing a line under all of that, we've got discrete basis sets and continuous basis sets. For a Hamiltonian, for a particle in a box, and for a system where there are boundary conditions, a Hamiltonian we're going to find will have discrete energy eigenvalues. Our position and momentum, however, those basis functions, that are a continuous set, not a discrete set. Okay, let me summarize all that. Operator, eigenvalue, let's just call it eigenvalue equation, and basis. And this is the table, and this table along the lines of what's in the notes as well. So we've got operator, momentum operator. I've added a section in the notes, by the way. A number of you have asked me why the derivative in terms of the momentum operator. It falls out directly, again, from, if we think about Fourier transforms and the relationship between the momentum representation of the wave function and the position representation of the wave function. I'm not going to go into it here. It's a bit of extra material for those you want to get an insight into that. For those of you who had just about enough of Fourier mathematics for now, just take that on board and run with it. So, our eigenvalue equation is we have a momentum operator operating on functions of the form e to the ikx, gives us back momentum and, of course, our eigenfunction, which you can see if you apply the momentum operator. And then our basis set, right, in terms of how we represent our wave function, or the position representation of our wave function. then our basis would be, or is, a Fourier transform, as I've just done. Can you see that? Okay, I think for a change you can see that. Okay, operator, eigenvalue equation, basis. So that's for our momentum, continuous basis. For a Hamiltonian, in the case where we don't have a free particle, i.e. for practically the much more interesting and useful cases, for a Hamiltonian, what we'll have is, what we represent this as? We'll represent those, where the UNs here are our energy eigenfunctions the Hamiltonian. Discrete. And indeed, the other thing as well is each one of these eigenfunctions is a stationary state. And our basis, in this case, we can write our wave function, and we've done this before, we've seen superpositions like this in a number of questions, where we've got some coefficients that tell us how much of each eigenfunction we need in the mix. So, there's a difference between a continuous basis and a discrete basis. So we've done momentum, we've done energy, the Hamiltonian operator, we've talked about position, but I haven't talked about what we have for the eigenfunctions for position. We've talked about the position operator, which is just basically x. We multiply the wave function by x. Let me explain what that means in terms of the basis function. Our position operator is simply x. Now when we operate on our wave function with the position operator, and this is true for any application of any operator, but what we do is we collapse the wave function. And for the case of the position operator, what happens is, let's think we've got some superposition. Again, you could think of the particle in a box, whichever you like. Let's make a particle in a box, so constrained to 0 at both ends. And we've got at some moment in time, we've got some set of eigenstates summing up to form a superposition, and we're getting some wave function that looks like that. We make a measurement. What happens? Well, if we make a measurement, it's not probabilistic anymore. We've made that measurement, therefore we know whether at that particular instant, and directly, very, very directly after that measurement, before the system has time to evolve, we know where the particle is. And it's there. It's at A, or there, or there, or there, or wherever. But let's assume it's there. So as for every other measurement, what we've done is we've collapsed the wave function into an eigenstate of the operator. That's what happens with every measurement we do. When we make a measurement with a particular operator, what happens is that the wave function, whatever superposition it might be, whatever time evolution state it might be in, it's merrily evolving away nicely, linearly and deterministically according to the Schrödinger equation. We make a measurement and bang! What we do is we collapse the wave function into an eigenstate of that operator, with a certain probability based on the Born rule, which is in terms of the coefficients or the function that determines the mixture of eigenstates, whether it's a discrete or continuous basis. What is that eigenstate what is that eigenfunction for position? Well, when we make that measurement, we know that the particle is here, or within a very, very narrow range, x to x plus dx. We know it's there. And our eigenstate, therefore, for our position measurement, is that trusty old delta function again. let me do it like this. That's x0. Assuming we've made a measurement, we found it at x0. Our eigenstate, our eigenfunction that the system is now in, because we know it's there, is delta x minus x0. Okay, a little sort of aside, and I also put this aside in the notes as well. Remember that a delta function is an idealization. We are in the land of frictional surfaces, no air resistance, if we're drawing analogies with classical physics. We are talking about idealizations. In any real system, of course, there's going to be a finite measurement resolution, which means that it won't exactly be in an it won't be in a delta function-like state. There will be some spread about that. But just as we don't bombard you with problems involving nasty elements of friction and working out, turbulent flow in terms of how something's falling, instead you assume that it's falling in a vacuum. In terms of the quantum mechanics, in terms of getting the principles across, it's much easier if we go with this idealization and think of it dropping into a particular state of complete certainty, which, and the way we represent that state is via a delta function. Okay, that's the little aside over. So our eigenstates our eigenfunctions for the position operator are delta functions. So let's write down an eigenvalue equation. Okay, so eigenvalue, and I've said that the eigenstates or eigenfunctions are delta functions. So now, if some of you are going, hang on, didn't you tell us a while back that we shouldn't really write delta functions outside the confines of a nice cozy integral, because otherwise you're mucking around with infinities in a bit of a way that makes us all queasy? Agree entirely. Unfortunately, this is the standard way, and in terms of the way we write down this eigenvalue problem, it does hold out. Let's put our integrals back in place. I understand your queasiness. I share your queasiness. Obviously, that's integrated over dx, and that's integrated over dx. So we do this. What will we get on this side? X0. We do this. Well, there are two ways of looking at this. We could pull the x0 out because it's a constant, and then just integrate this, and then that would be 1. So x0 will be equal to x0. But the other way, slightly better way of thinking about it in terms of the eigenvalue problem, is that if we think about, our wave function again, we've measured this is x0, delta x minus x0. Now if we have our function, which is basically just that point, x0, and we do another integral like this, where this is our eigenfunction, then that sifting out x0 is going to give us x0, which is why we write our eigenvalue equation and why we take our eigenfunctions to be delta functions. No, not that. That. Right, making it real again. So, I have asked you throughout the notes to just accept as a matter of faith, basically, that the operators we're using, in terms of the Hamiltonian, in terms of the position, momentum operators, and all other operators in quantum mechanics, return real eigenvalues. That's true. I haven't been lying to you, but I haven't given you any indication of why that's the case. So, for those operators to return real eigenvalues, it means that this condition must be true. If we've got an arbitrary operator O, and the expectation value is that, then it must mean, if it's returning real eigenvalues, that the expectation value is the same as the complex conjugate of the expectation value. So, in turn, that means that in terms of the integral we use to calculate the expectation value, now let me put this up here. So what we have, this side, thinking about this first of all, using the standard formula, the standard integral we've used before many times. I'm keeping it in one dimension. Everything I'm talking about here in one dimension translates to higher dimensions. But just keeping it in one dimension keeps things clearer. So let's do that this side, and we're going to take the complex conjugate across the board. So what we'll have is that complex conjugate of that, and then complex conjugate of that. All I've done is take this side and get the complex conjugate. Now, the operators that are used to return real eigenvalues are called Hermitian operators, as I may have mentioned. And Hermitian operators, for reasons I won't go into just yet, we will return to this when we get onto the matrix mechanics part of the course a little bit further down the line. But Hermitian operators are associated with basis sets, eigenfunctions, where the eigenfunctions are happily orthogonal to each other. And we've exploited orthogonality quite a number of times thus far in a number of the worksheet problems and elsewhere in the module. We're going to write a standard eigenvalue equation. So operator operating on our wave function, on our eigenfunction, returns an eigenvalue times the eigenfunction. So we know that. We're going to do a little bit of a trick now, a little bit of a mathematical trick that is going to show us that eigenvalues associated with this operator, which we're assuming to be Hermitian, will return real eigenvalues. So what we're going to do, and this is to relate it back to the integral for the expectation value, what we're going to do is we're going to multiply both sides. We're going to take another eigenfunction, we're going to call that psi m, and we're going to take the complex conjugate of that. And we're just going to multiply both sides by that. Just a little trick, the reason for which will become clear soon. We can do something else, which is that we can write similar expression in terms of the complex conjugate of the operator, where anywhere in the operator we've got an I, we change it to minus I. Let's write it like this. So we've got that. Now what we're going to do is we're going to multiply both sides of this by psi n. Okay? Now, possibly you might be able to deduce where this is going. So this, you might notice, is in the type of form we had in the integral for the expectation value. What we're going to do now is we're going to subtract this from this, and we're going to integrate. Is between minus infinity and infinity. And we're going to integrate both sides. Minus this, but we're integrating between those limits again. Okay, so look at what we have here. So we have complex conjugate of psi m and psi n. We have the complex conjugate of psi m and psi n. So what we have, if we're subtracting this from this, will be that's equal to On minus Om star times psi m star, again between those limits, psi n dx. I will probably put the integral up in, I'll just put a GIF of the integral on the screen so you can see that better. Now we've assumed, we'll come back to this later on as I said, but we've assumed that our eigenfunctions for Hermitian operators are orthogonal. That's quite neat because that means this will disappear anywhere where m is not equal to n. So if m not equal to n, that side's 0, then that equals 0. That means that this will be On minus On star. because we're setting n equal to m. If our condition is for real eigenvalues, which it is, then this will be 0. Doesn't matter if we've got n equal to m or if we don't have m equal to n, that side's going to be 0. So let's do that. Which in turn means, and this is our condition for Hermitian operators, which will give us real eigenvalues. That's a minus sign, remember. And we can write it like that. So that's the condition for our operator to be Hermitian, and therefore for our operator to return eigenvalues. We've made one key assumption there in deriving that. We've assumed orthogonality of our eigenfunctions. Hermitian operators are associated with what are called complete basis sets, which are orthogonal. The eigenfunctions of which are orthogonal. We will be coming back to that. For now, I just wanted to give you that little bit of allay any concerns that I haven't been pulling the wool over your eyes, and that the eigenvalues associated with the operators we use, the Hermitian operators, are real eigenvalues. Okay, let's put that in the context of a concrete example. And given that we used the particle in a box before, let's use the particle in a box again. And let's consider the momentum operator in that context. This works whatever context we use, but let's put it in this context. In terms of what's called the hermiticity, the Hermitian nature of the operators. Okay, so in terms of the expressing the integral we had for the expectation value, we're going to go between the limits of 0 and L because particle in a box, and we are going to take an arbitrary function. Let's just assume, let's call it f of x. It could be anything, but just to show you the sort of universal nature of this, let's call it f of x, and we have our momentum operator, which is minus I h bar d dx. Sorry, that should be the complex conjugate operating on fx, and then we integrate that up. Okay, so I put the specific dependence on x in. That's just to simplify the algebra a little bit. Let's just write that like that. Take the minus I h bar outside, and then we have df dx. Okay, we're going to have to integrate this by parts. So what we'll have is minus, and it's important not to drop minus sign, so I'll do this slowly. So what we'll have here, so that would be between limits 0 and L minus, and that's outside, so minus in terms of integration by parts, so that would be between 0 and L, and this will be f d u dv. And let's just put that on the other side. Can you see that? Is that all on the board? I think it is. Good. Right, this goes because the wave function vanishes at x equal to 0 and x equal to L, so that can go. Then we've got negative by a positive, get rid of that, take that over there. That gives us an IH bar, and we're left with that integral. What's so important about that integral? Well, remember that what we're trying to show that the momentum operator is Hermitian, which means that we'll stick with f. And we'll put it in like that. And then it's going to be that's a condition for the operator to be Hermitian. So we've basically done this integral and shown it's this. And let's fill in the rest here. So that's on this side, that's f putting in our complex conjugate of our operator. So it's minus IH minus IH bar ddx. Complex conjugate of that will be plus IH bar. Let's take that outside. ddx which is exactly that. So we've shown that that's equal to that, which in turn is exactly the same as the other side. So we fulfill the condition for the momentum operator to be Hermitian. You can do it for all the other operators. You'll find each time that the operator is Hermitian and therefore is associated with real eigenvalues. Okay, a bit of a coda. I did say I wasn't going to do this, I'd just leave it in the notes, but I'm just going to take a couple of minutes to show the momentum operator, what the momentum operator looks like, not in position space, not in terms of minus IH ddx, but what it looks like in momentum space, and to show that the derivative that we use, the differential operator, that we use for the position representation, turns out that that's just a multiplication when it comes to momentum space. We've got, as we've seen a gazillion times for Fourier transforms, we've got this relationship between position and momentum. They're equivalent representations. So if we are using a position operator in position space, which is just we multiply by x, we would think that in momentum space, if we've got the momentum representation and we want to find the momentum, we want to operate to find the momentum in momentum space, that it would just also be a multiplication. We'd expect that because they're equivalent representations. It's just that we're thinking about it either in terms of position or momentum, but it's still just different ways of looking at that wave function. And the remarkable thing is that a differentiation in terms of x turns out to be a product, turns out to be a multiplication in terms of the Fourier transform. It's really neat and really mathematically elegant. I'm not going to examine you on this, but if you're interested and you want to understand just the links between the position and momentum representation, I think this will help you just get your heads around what the operators are doing, and again give you a little bit more insight in terms of position and momentum. Or if you're incredibly masochistic and just like me love Fourier transforms, this is for you. So we wrote that before that we can represent our wave function in terms of the momentum representation. Looks like this. It's a Fourier transform. Right? Continuous basis set. This is the function that tells us the mixtures of all the different basis functions that we need to represent our wave function. You've seen, I've given you code and talked you through the Python code to calculate the Fourier transform. Use that code. Play around with functions. If you're finding it difficult to get your head around this, you can just put in the function you need, Fourier transform it in the code, and see the Fourier transform, see the momentum representation. It's, I think, much more powerful to do it that way, whereby you sort of get an instantaneous, there's a plot on the screen, rather than a formula after churning through 4 pages of maths. Of course, we have to do the maths, and there's a reason for doing the analytical maths, but in terms of visualizing this stuff, using some Python code can help you along. Anyway, so watch this is neat. So we're going to now, a momentum operator on the wave function, the position representation of the wave function, involves a derivative. So let's do the derivative. But we're differentiating that, so let's just differentiate both sides. So it's 1 over root 2 pi. This only depends on k, so all intents and purposes that's a constant, because it only depends on k. This, however, depends on x. So what we're going to do is we're going to differentiate that. Okay, so all I've done, oh no, that was naughty, there we go. ddx. Okay, so we're going to differentiate that. What are we going to get? Well, we're going to get this. Ik e to the I kx dk. Which in turn, let me clean the board and put it up the top here. Okay, why have I put square brackets around that? I want to make it very, very clear that if psi k is the Fourier transform of psi x, I k psi k, that bit, it's the product of this by our basis functions. So this bit, the bit that's multiplying into this, is the Fourier transform of this. So, Fourier transform, let's write it like this, of d psi dx is ik times the Fourier transform psi k. So it's a subtle argument. It's a slightly subtle argument, but basically, if we just have psi here, then we just have psi k here. Now, the important thing is that the Fourier transform we need is whatever multiplies through on these basis functions. So that means that the Fourier transform of d psi dx is ik times the Fourier transform of psi x. So what's happened, and this is a standard result in Fourier transforms and Fourier analysis, it's not just a quantum thing, it's a standard result. We could just as well be talking about radio signals or NMR signals or I don't know, water waves or whatever you like. Anytime we want to take a Fourier transform of a signal or a bloody Slayer album, whatever, the result holds. In that, what happens is that differentiation in position space, in this case, is a multiplication in momentum space. So that's good, but let's keep going. So that means in terms of our operator in momentum space, so that's the d psi dx. What happens now if we put in the other bit? Well, minus I h bar d psi dx defines our operator. Multiply this by I h bar, and what we'll have, oh, this is so neat, h bar k, psi k. And what's h bar k? Well, h bar k is p. So, just as we have, if we consider the position operator in position space, or the position representation of the wave function, we just multiply through by x. Similarly, if we're talking about the momentum representation, which is the Fourier transform of the position representation, we just multiply through by p to get the momentum. It's a really elegant result that falls out of a few lines of Fourier analysis. You're not going to be examined on this, so don't panic if it doesn't make sense. If it makes even a little bit of sense, that's great. And if, like me, you share that masochistic bent with regard to Fourier transforms, I hope you got something out of this. Okay, onwards and upwards, and the next video is all about the wonderful act of measurement. See you then.